Thanks for letting me know. Whoever that was that Marion?
It was me. Okay.
Okay.
Thank you.
Thank you. I appreciate you catching that. Man, I don't know what's that. I got to go back and check all my settings on Zoom. So, as we were saying, a battery is just essentially a pile of dissimilar metals connected by some kind of fluid solution that allows charges to go from one metal to the other. This is a typical diagram of a battery with a zinc cup that's all covered except the very bottom, and then a carbon terminal that goes all the way through this paste, and then it's covered with a little metal on top, and that metal is the positive electrode. This one's a negative. And like I said, connecting it to something like a light bulb would be basically just running a wire from the positive to one of the terminals of the light bulb, and then from the other terminal of the light bulb to the negative. As far as the light bulb goes, though, one terminal is the actual thread part, and then the other terminal is actually the little speck of metal at the very bottom, usually separated from the actual thread by like a little piece of black glass or something like that. Basically, this little end might be connected to this end of the wire, and this end is connected to the threads. So we could draw it like this, but in reality, most circuits, when we connect them, we just connect the battery up to some load, which could be a fan, it could be a heater, it could be a light bulb, it could be your iPod, your iPhone, or whatever, and then you return that wire back to the negative end. It's almost like you pretend little positive charges, and I say pretend for a reason, but you pretend little positive charges are leaving, and they ride all around and go through this and then come back, and if you don't have a source for them to come back, you're going to run out of charges. And I say that's pretending because in reality, it turns out you really don't exchange very many charges from the wire to the battery. It just sort of compels the charges to move in that wire. So what I was talking about with this circuit was specifically, we have the negative side of the battery. I'm going to assume that the black wire of a voltmeter is attached to this negative side of this battery, which would be this part down here. And I connect the red wire to just above, just the positive terminal, which is this part right here of the battery, and this would read the voltage at that point. Well, that voltage, if that's a AA or something like that, should read 1.5 volts. Okay. What you'd find out though is as you go around here, there's actually some resistance in the wire itself. Now the wire's resistance is probably super small compared to say the light bulb or the heater or whatever you have, but still in reality this is like 1.499999. And by the time it gets here, right, it might be 1.4999 instead of 12 nines, because what's going on is the energy per unit charge, which is what we call the electric potential, is decreasing as you go along this wire. And once you hit the big charge, then what's going to happen are the big resistance, which is what this load is, then it's going to drop a lot. So it's going to go from 1.499 to, let's say, 0.00001. So now what we have, again, the black part will be over here to the 0, but if I tap this part with the red end of the voltmeter, this will be 1.49999, say, if you actually had a voltmeter that could read that well. And I know I wrote that really small. It doesn't really matter how many nines I got. The main thing is it's really close to 1.5, but that you recognize it being smaller. Now, if I do, again, black terminal to this spot and red terminal to this spot, then you're going to read 0.00001 volt here. Meaning basically the lion's share of the energy per unit charge drop took place across that load, because that load is the biggest thing in the circuit. Now it's going to stay 0.001, and maybe it goes down a little bit until exactly here it reaches exactly 0 volts. Okay, so that's really what's going on inside of a typical very simple circuit. What we need to know is things like how much flow charges or appears to be how much flow charges flow, how much charge flows or appears to flow from this battery through this wire. The amount of charge flow, which literally means the number of charges, say, that go through this line right here per second. That's the flow of charge. If I could literally count the number of coulombs that went through here every second, I would then be able to tell you what the charge flow is. And that charge flow is called current, electric current. The voltage we've already talked about. That's, remember, the potential energy per unit charge. So it's just like potential energy, but we're using a special unit. We're taking out the charge, which would be the charge of the thing that's affected by it. Now I've just introduced another concept, which we use the symbol I for, and that's current. And that is generally the change in charge per time. So if you were counting the number of coulombs that went by a given point in a circuit and dividing it by the amount of time it took for that number of coulombs to go by, you would get a certain number of coulombs per second, which is defined to be the ampere, which we abbreviate with just A. Okay, so those are two big parameters, and we ultimately want to know, how does this change? In other words, what do these two parameters depend on? I know I can build a battery that has a 1.5 volt voltage, and I know that's going to force a certain number of coulombs to go through this little part of the circuit per second. But what does that really depend on? Well, it turns out it depends on this thing right here, which is called a resistance, and we normally give that the symbol R. So that's R equals resistance. And then there's a law that relates them, and it's called Ohm's law. So Ohm's law says that if you have a given voltage V applied across a resistance like it is here, okay, then the current through that resistance, I, multiplied by the resistance R of that resistance, will be equal to the voltage. So in reality, the voltage for this thing was 1.5. Let's use this number instead of the funky real one. Let's say it's 1.5. Basically, because this had a little bit of resistance, this wire, that's why the voltage went down a little bit, because basically you took the current going through it and multiplied it by that itty bitty resistance and got, you know, this itty bitty difference between 1.5 and 1.4999. Okay, but this is called Ohm's law, and it allows you to calculate the voltage drop or increase across any object if you got a certain current going through it, I. From that, you can see that R is equal to V over I, and V, remember, has a unit of volts, and I has unit of coulombs per second, or amperes, which is also a volt per amp, and the volt per amp is defined to be the ohm, which is given that symbol. You might have seen this before, especially if you're in a fraternity or a sorority or just taking physics classes. But you also might remember it from the New Testament. I am the Alpha and the Omega, because the New Testament was written in Greek. So when it says I am the Alpha and the Omega, it means I am the beginning and the end, which obviously Alpha is the beginning of the Greek alphabet and Omega is the end of the Greek alphabet. So Omega, cut off the Aga part and you just get Ohm. Okay, so those are the units we're using, and this is Ohm's law. It's not that, it's really a very simple equation to use. We just need a couple of examples to show you that. So first off, let's imagine a current of, let's say, 1.00 amps is flowing through a wire. And let's say that it flows for 3.00 minutes. Okay. What I would like to know is how much total charge passes a given point in that time. That's part A. So I want to know in that 3-minute period, how much charge actually passes through a single point like that line I drew on the circuit earlier. I'd also want to know how many electrons that would be. How many electrons would that require? So this is us working with the idea of current first before I touch an actual Ohm's law problem. So what we know is I is equal to the amount of charge that flows divided by the time taken. We want to know the amount of charge that flows, so that has to be I times delta T. Well, I is 1.00 amps, but this is a good time for us to recall that an amp is a coulomb per second. And I also know that 3 minutes is how many seconds, anyone? Well, how many seconds are in a single minute?
It would be 180.
It's 180.
There you go. Yeah, because it's 60 seconds per minute and times 3, that'd be 180 exactly. So I'm going to say 180 seconds because it's 3 minutes, and obviously 180 times 1 gives me 180 coulombs. That's a buttload of coulombs. Remember, we're talking about a lightning strike at this point. Remember, lightning strikes, I said it's not uncommon for a lightning strike to transfer on the order of 100 coulombs. So yeah, that's a lot. Now part B, that was part A. Part B, we want to know, well, how many electrons will that? Well, the number of electrons, I think you'll understand, is actually equal to the amount of charge divided by the charge per electron. I should write this as Q per electron. Okay, so if I divide the total charge, which is 180 coulombs, by the charge that each electron has, then that should give me the number of electrons. So I'm going to take 180 coulombs, and I'm going to divide it by 1.602 times 10 to the negative 19th coulombs per electron. Notice how I wrote that, coulombs, and then I wrote per electron. If you sometimes take a number like that, like the charge of the proton is 1.602 times 10 to the negative 19th coulombs per proton, or if you do that for the electron like I just did, then it'll actually allow you to think out how to do the problem. It wouldn't make any sense, for instance, to call this number 1.602 times 10 to the negative 19th electrons per coulomb. So you know the unit's supposed to be a coulomb, so it actually can be thought of as coulombs per electron. And when you divide coulombs by coulombs per electron, the coulombs actually cancel out and leaving nothing but the number of electrons. So all I have to do is divide 180 by 1.602 negative 19. And I get 1.123, or 1.12 times 10 to the 21st E minuses. So in reality, that current, which is 1 amp, which like I told you before, an amp's actually a big current. That's more than enough to kill you. It takes on the order of milliamps to kill you. So a whole 1 amp really requires about a 1.12 times 10 to the 21st electrons. That's about 1 with 21 zeros after it electrons to pass by in a single 3-minute interval. That, by the way, is about, I don't know, about 100th of Avogadro's number. So it's about 100th of a mole of electrons. So that, again, gives you an idea of how big a mole is, or, you know, how big Avogadro's number is. So any questions on that? Okay, so now I want to do an example with Ohm's law, and I'm going to talk about basically like a flashlight. Let's say a flashlight has 2 AA batteries in it. So we have a flashlight. So it's a little flashlight. It's got a AA battery stacked on top of a AA battery, so that the total voltage V is about 3.0 volts. Okay, and let's say it draws, I don't know, let's say it draws 200 milliamps of current. So I might want to know, what is the resistance of the light bulb? So I'll call it R sub LB. That's a typical question. What does the resistance appear to be of a light bulb? Now remember, I've told you before that light bulbs are this neat little thing. Like when you first connect them, they have one resistance, but the longer they stay connected, the hotter they get. In fact, a regular light bulb, it's the very fact that it's getting hot is what's making the light. So basically, as you first connect it, the wire gets hotter and hotter and hotter until it reaches that temperature where the radiation that it emits is in the visible spectrum. Until then, it doesn't light up. But once it gets hot enough that it's emitting radiation in the visible spectrum, then we see it as actual light. And as it gets hotter and hotter, the individual particles, basically the atoms or molecules making up the metal, and the individual electrons themselves are all jiggling very, 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 very fast. And the hotter it gets, the faster they go. So it's harder and harder for an electron to make its way through there. And that's why the resistance goes up. What we want to do is now calculate in part A, what is the resistance of the light bulb? And then in part B, let's consider what would happen if the battery started to die. So what happens when a battery dies is you sort of treat a battery as if it's this perfect battery next to a little resistance. But as the battery gets older and older, that little resistance gets bigger and bigger. And over time, that causes the voltage at the terminals, which, like I told you, started normally at 1.62. It'll slowly drop to 1.5, which is okay because you can still use it, but eventually it'll drop to say 1.3 or something like that. So let's say if the voltage drops to 1.3, what would be the current provided to the light bulb? In other words, can we see anything from the light bulb that would suggest it's dying? So in part A, we're going to use Ohm's law, V equals IR, and we just want to calculate R. So R is going to equal V over I. V is 3.0 volts, and A, or I, is should be in amps, not milliamps. So it's 200 times 10 to the negative third. I can get rid of that 10 to the negative third by moving it 1, 2, 3 places to the left. So that's 0.200 amps. So that's really what 200 milliamps is. It's 0.2 amps. And that helps me because you know how I hate using my calculator. So I'm going to do 3 divided by 2/10. That's the same thing as 30 divided by 2. And that gives me 15 ohms. And technically with sig figs, that works just fine because I said it was 3.0 volts. If I'd said it was 3.00 volts, I'd probably need to call that 15.0. But since I said 3.0 volts, that should be fine. Now B, let's imagine that the batteries have gone kind of crappy and they're no longer 1.5 volts. They're now down to 1.3 volts. what's the actual current delivered to the battery now? Because in fact, if the current's not high enough, it's not going to make the metal hot enough that it produces any light at all. And until then, it's actually going to be, instead of that pretty white light that you get from a typical incandescent light bulb, it's going to be sort of a ruddy orangish red crap. So let's see what that current is. Well, if we assume it is ohmic, and again, that's a very a very problematic assumption. It's not likely that this 15 ohms is always going to be the same. It's going to be a different value, in fact, for each temperature. But we're going to just, as a first order approximation, estimate what the current should be, given that the resistance is exactly 15 ohms. So in this case, we're going to solve for I, and I is equal to V over R. And we said the voltage is going to be 1.3 volts. And the resistance is going to be 15 ohms. So I'm going to use my calculator on this. I just started thinking about cool fractions that I could use for that and realized that would really suck for you guys. So let's say 1.3 divided by 15 equals 0.086. 0.08, and it's actually 666666, so I'm going to call that 0.87 amps. So instead of getting the, what did I use before, 200 milliamps, now I'm going to get like 87 milliamps. 87 milliamps might be enough to actually cause it to glow that ruddy red color, sort of the same color you'd see from, let's say, a horseshoe stake you threw in a bonfire. After a certain period of time, it looked kind of ruddy red, and if you kept it in there for a long time, it would turn sort of white hot, especially if you have a really, really hot fire. So this is really what's going on with a battery as it dies. Any questions on that? Okay, so that's a very typical Ohm's law problem. You'll see Ohm's law problems all the time. One thing you might want to keep in mind is if you have a volt and you divide it by a kilo ohm, you don't have to take the time to convert that to ohms. You can just realize that a volt divided by a kilo is actually a millivolt, and since you're doing a volt divided by ohm, it would actually be a milliamp. So if this was supposed to be 15 kilo ohms, then I would put 15 kilo ohms, and then instead of this coming out as 0.087 amps, it'd come out as 0.087 milliamps. So that can save you a little bit of trouble. Things like that. Also, when you have a milliamp, in this case, so you had a milliamp multiplied by a kilo ohm, the milli, which is times 10 to the negative third, and the kilo, which is times 10 to the positive third, those two cancel out and just give you an actual volt. So you don't always have to flip back and forth between milli and kilo as long as you pay attention to what's going on. So for instance, a volt divided by a milli, that's a 10 to the negative third in the bottom. And if you remember from algebra, you can make that exponent positive by moving it to the top. Or in the case of a kilo down here, you can make that exponent negative by moving it to the top. So this was 15 times 10 to the third. If I pull it up here, it becomes 1.3 times 10 to the negative third. That's why I said it would be milli. So that's just a little trick you can use. You're not required to use. I just let you know sometimes that'll save you a little bit of time. Does anybody have any questions on any of that stuff so far? Okay, the things I missed, I seem to have all caught up with regards to the chat. So that's a good thing. Not seeing anything else. Well, let's keep pressing on then. When you actually try to think about what is Ohm's law, a very typical lab that's done is the Ohm's law lab. In fact, that's what we're going to do. And the Ohm's law lab basically just allows you to establish Ohm's law. Ohm's law says that voltage is equal to current times resistance. So what that means is if you take a circuit like the one I drew before, and we start connecting a resistance to it. So here's our battery. It has a voltage V. And maybe we would use, in a typical classroom, we actually use a voltage source as opposed to a single battery, because that allows us to put in 1 volt, 2 volt, 3 volts, 4 volts, 4.5 volts, whatever. And then I could apply that across a single resistance R, and that R could change too, but for one experiment to look at Ohm's law, we're probably going to keep the same R, but vary V. And then we're going to actually have to measure the current through it so that we can actually get a relationship between current and voltage. And when you do that, you have to use an ammeter. And an ammeter is this neat device where you actually have to break the circuit and have the wire, every little bit of electrons that run through this resistance have to go through the meter in order for you to measure current. So that's the way you have to connect an ammeter. And this will read a certain number of amps. And then the negative side, the wire comes out from here and goes back to the battery like that. So that's the way you'd have to hook up a circuit to measure amperage. And you could also just take a voltmeter, which would look like this. It would also have a positive and a negative. So the positive is normally red and the black's normally black, or excuse me, the negative is normally black. But the cool thing is about a voltmeter is you only have to connect it in parallel to the thing. You don't have to break the circuit apart. So I can just take this positive terminal and connect it right there, and I can take this negative terminal and connect it right there, and that would tell me the voltage of the battery. Since we're ignoring the small resistance of the wire, that should be the same as if I connected this wire all the way to there. Remember, I showed you this would maybe be 1.5, whereas this would be 1.4999. Well, your voltmeter is not going to measure 1.499. It's going to call it 1.5. And your voltmeter is not going to measure 0.00001. It's just going to call it 0. So putting it here, if the wire resistances are very, very small compared to this, then clearly the voltage here is very close to the same as the voltage here, and the voltage here is very close to the same as the voltage there. Does that make sense? And when I say very close, like a typical wire might have a maybe a 1 ohm per meter resistivity. What that means is basically for every meter of it, it's only going to have a resistance of 1 ohm. So you usually use less than a meter to get from here to there. And this resistance is normally going to be like 30 kilo ohms or something like that. So 30,000 compared to 1 is certainly means the 1 is insignificant. So that's how you'd actually physically in a lab set up a circuit to determine Ohm's law. Then what you do is you'd make a graph of voltage versus current. And if Ohm's law is right, we know that the equation for a straight line is y equals mx plus b, where this is the slope and this is the y-intercept, right? Well, I must look that bad there. Okay. Well, in the equation V equals IR, this is the role of X, the I is, and V is playing the role of Y. So R is more like the M, and there should be no B. So all of that is a test on whether Ohm's law is right. So if you make a plot of the resistances and voltage, then you do a line of best fit. It better look something like that. And this is the reason that I said we won't change our resistances. And the slope should be equal to the actual resistance. So that's a wonderful experiment you can do to test whether Ohm's law is correct. You can even do things like try different resistances, do another graph for that, and maybe your other resistance gets a different slope, and that slope better match it too, that sort of thing. So once you do all that, you're then pretty confident that Ohm's law is accurate. But then you can do something like a light bulb, which I warned you about, and a light bulb, if you do it properly, will tend to have a line that looks like this. Because what's happening is the slope is very low down here because the current's so low it doesn't get very hot. But as the current gets higher and higher, the resistor gets hotter and hotter, and therefore the resistance gets higher and higher. And in fact, it starts to go towards infinity. So that's the actual curve for a light bulb. So I'll just label that LB for light bulb. Whereas these two are what we call ohmic devices. OHMIC. So they're ohmic devices. When you're in the lab, it turns out that an actual resistor will normally look like this. It'll have a wire sticking out and another wire sticking out the other end. Usually it's quite long. And then it'll have 4 stripes. Sometimes it'll have 3. It'll have 4 stripes. And each of these colors of these stripes, you can look up in a table and it tells you what its value is. So these two would tell you the 2 main numbers for the resistance, like a 2 and a 3. And this would tell you the multiplier. So it would be like you could look up one color and it might say 1,000. So if this was a 2, a 3, and 1,000, this would be 23,000 ohms. And this tells you how precise it is. So for instance, one color means plus or minus 5%, one color means plus or minus 10% or 20% or something like that. So that's really how the resistors look in reality. And you can see them, like if you ever have to open up any electronic device you have, you will see actual things that look just like this. And they're usually like soldered to this little green board. And you'll see the little device looking like this, and then the wire, there's your stripes. And the wire then sinks back down into the little green board. That's what they ultimately look like, but like I said, on a green board with a bunch of things. So those are resistors. The capacitors we looked at earlier, or we talked about earlier, they'll look like this sometimes. And they'll have 2 little wires sticking out, and they would actually be stuck into a little green board as well. Some other ones look like this little fat on here, and then a little wire sticking out like that, and a wire sticking out like that. So they kind of look like Kirby. Those are another type of capacitor. So these are some things that, like I said, if we were face to face, I'd be pulling these things out and showing them to you. The textbooks always give you photographs of these things, so definitely look at them there. But I just want you to have some idea of what they look like in everyday life. I've even saved myself a lot of money by making repairs on, very expensive televisions and stuff. There's some danger to it, so by all means, don't take that or consider that lightly. In fact, I almost killed myself with the flat screen TV that I repaired because I touched the wire that I was touching. Also, the screwdriver touched at the same time a heat sink, and it sort of welded the screwdriver to the heat sink because there was a huge current ran through it. Now, had I actually touched that with my finger as opposed to the screwdriver, I may not be here today. So it's a very, very dangerous thing. But the cool part was I found one of these that had a little top. They have like a little Mercedes symbol on top. So like this and this. And when it goes bad, that little symbol pops up. Well, it popped up, and lo and behold, I looked at it, and it was exactly a capacitor that I already had in my toolbox. So I just cut it loose and soldered a new one in place. The TV worked fine. It literally cost me zero. This capacitor probably would have cost, for a pack of 20, probably would have cost $5 or maybe even a couple dollars. And it cost me, like I said, essentially nothing. Well, except for the risk of dying. But other than the risk of dying, I saved a lot of money because I think it was $175 service call for them just to come out. So sometimes you can get lucky with stuff like that. Just like I said, don't assume that you can open stuff up and not be killed, especially with TV. Even when you unplug it. So like if you try to work on a washing machine or a dryer or something like that, there's a lot of electronic components, the capacitor being the main one, that keep the voltage alive even though you no longer have it plugged in. So you're not necessarily safe working on a TV or something like that just because you unplugged it. So don't ever go into it with that idea. But anyways, once you know some stuff, you can become very dangerous. Once you know a lot more, then you can keep yourself from dying. Okay. All right, so like I told you, the resistors, when you find one, you try to spec it, you can tell what its strength is, i.e. what its ohm value is, by reading the little stripes. And then what we need to think about is how do these resistivity, or how does this resistance stack up? For instance, what if I use, in place of a resistor, what if I used a wire that's made out of a crappy iron metal instead of like something like copper? So that brings us to the next concept, which is resistivity. So it turns out you could have a couple choices, and I'm going to ask you about these because I really want you guys to see if this makes perfect sense to you or not. Let's imagine that you have to go from one end of a wire to the other. And this is one of the wires you have to go through. And then this is the other wire you have to go through. Notice they're essentially the same length. Which one do you think it's easier to go through for, let's say, any number of electrons to make a current? Do you think this one's easier to go through or that one's easier to go through? The top or the bottom? Yes, Charles said the top. That's exactly right. It turns out it's not unlike, being at a party, and if you got a 3-foot wide hallway you're walking through, it's going to take you a long time to get from one end of the hallway to the other. Whereas if you got a 12-foot wide hallway, you can do it pretty well. Only this is not a one-dimensional problem like a hallway walking is, because the electrons can sort of walk along the walls too. So it's actually the whole surface area that matters. So what we see is that the resistance of a wire, based on your own conclusions that you made, resistance, remember, is the thing that makes it harder to go through. We should expect it to go down the bigger the wire is. So I'm going to say resistance is inversely proportional to the area A. And by area, I mean that cross-sectional area right there, which is the same as this one. And I literally mean like square meters, square inches, that sort of thing. Now, let's consider this wire and this other wire. So this wire and this other wire have the exact same area, but this other wire is like twice as long. Which one do you think is easier to go through then? The middle one or the bottom one?
The middle.
The middle, yes, because it doesn't have to go as far, right? So we'd also expect the resistivity, or the resistance, excuse me, I keep saying resistivity. The resistance is going to be directly proportional to the length, meaning if I double the length, I'm going to double how hard it is to get through. So I'll put an L like that. Well, once you establish that, it's just, duh, this is common sense. You expect the resistance to be directly related to L. If I double the length, I double the resistance. It should be inversely proportional to A. If I double the area, I cut the resistance in half. If I triple the area, I cut it in a third, so on and so forth. That's pretty much common sense. But then when you're all said and done, you can have two wires, one sort of silverish and one sort of goldish looking, and they're identical other than the color. And lo and behold, the resistances are different. So we need another parameter that takes into account not necessarily color, but what the stuff is made of. So it turns out that last parameter is called the resistivity. And it's given the symbol rho. So that's the Greek letter for R. And in fact, if you're typing in Microsoft Word, you can type a lowercase r, highlight it, and then change your font to symbol, SYMBOL, and it will give you exactly what the rho looks like. And that's true for all the alphabet, by the way. You'll get Greek letters for them. And once you introduce that, you see that R is equal to resistivity times length over area. And that, gives you some ideas about things in everyday life. For instance, if you're wanting to wire up a stereo, you've got a certain power output that your stereo or your iPod or whatever is able to put out. If you have to waste a good fraction of that power on wires going 50 feet across the room, then obviously it's not going to be as loud. So if you could actually put your speakers closer to the unit, then you'd get more power output from the individual speakers. So little stuff like that helps. However, if you have to go 50 feet, maybe it would be better, instead of using a really, really small gauge or really, really small radius wire, to use a higher radius wire, in which case the A goes up so the resistance goes down. Maybe you can compensate for that 50 feet length by making it, say, 10 times bigger in diameter. So all of that's a possibility. Let me give you a certain scenario. So let me say I'm going to consider we have remote speakers and the wires connecting them. So let's say we are to connect wires speaker wires. And I'm going to say they're 30 meters long. To our stereo. If you want the wire, so if I want the wires to have a resistance of less than let's say 1 ohm total. That means 2 speaker and back. How big should the diameter be if copper wire is used? So we're going to connect the speaker. So basically what that means is we got a stereo. It's got a little, basically 2 connections. There's wires going to run all the way out to a speaker, and then it's going to have to run all the way back. Like I said, with everything that's power. I know you don't see those words. We address that. So we got the speaker out here. Here's the output from our stereo. A wire's got to feed the electrons basically to the speaker. Okay, and then of course that wire's got to bring back some of those electrons, sort of an idea anyways. So what we want to know is how can I keep that total resistance of that wire less than 1 ohm? So I want R less than 1 ohm. I want the resistivity to be the resistivity of copper. And it turns out the resistivity of copper is 1.68. This is something that either we would give you a table or I'd have to give you the number specifically that you needed. But normally we give it to you in a table, and we give you several tables, so you got to know which one to use. But it's 1.68 times 10 to the negative 8 ohms times meters. Notice this has to come out in ohms. This would be meters squared, and this would be meters. So meters over meters squared just gives 1 over meters. So this has to have units of ohms to make that, but it also has to have a unit of meter to get rid of the meter that's left from down here. So the unit has to come out in ohm meters. So what I want to know, I know the L is going to be, in this case, I said 30 meters. Is that the right length that we're going to have to use? Anyone?
Would you use 60 instead?
Yeah, you'd want to use 60 because you got to go all the way there and then all the way back. Exactly. And then finally, what we want to know is the diameter equals question mark. Okay. So one thing we know is the area is equal to pi r squared, but remember that r is actually radius, not resistance. So you got to get kind of be careful with that. But you do know that radius is the diameter divided by 2. So I can change that to d over 2 squared. And then I get a lot simpler expression that doesn't confuse me with my r's. And that's pi over 4 d squared. So plugging that in, we got R equals rho L over A. I can now replace A with pi d squared over 4. So I'm going to say it's equal to rho, the 4 will be on top, the L over pi d squared. What I really want is D. So if I pull D over here, it'll be D squared is equal to 4 rho L over pi R. And then if I want to know the actual diameter instead of the square of the diameter, I got to take the square root. So that'd be 2, because the square root of 4 is 2. 2 times the square root rho L over pi R. Now, you don't have to solve it this way. You can just throw the numbers in, especially in the 202 class. That's often what's done. You can just throw the numbers in right here at this point and then solve for d squared. That's fine. The reason more advanced physics students and instructors do this is it gives us an expression that's true for all problems as opposed to just that one particular one. So if you throw the numbers here and get D, you got an answer for D in that particular problem. I've got an answer for D in every problem like this. I can see, for instance, that the diameter goes as the square root of the length. So if I double the length of the wire to compensate for that, I don't double the diameter. I actually only increase the diameter by about 1.414. If I quadruple the length, though, then I have to double the diameter. Similarly, I see it's inversely proportional to the square root of the resistance. So if I wanted my resistance, or if I found out the resistance went up by a factor of 4, the only way I could compensate for that is to decrease my, increase my diameter by a factor of 2. So that's why I do that. But putting all these numbers in, I get 2 times the square root 1.68 times 10 to the negative 8 ohm meters times 60 meters over pi times resistance, which should be less than 1 ohm. So less than, basically when this diameter comes out, if I got R any larger than that, then that would make the diameter smaller, but I want R no bigger than that. So in fact, I would have to make the diameter at least this big. So that's how you work out the difference between less than and equal to. Normally, it almost always happens that less than or less than and equal to, you just work out the equal to and then figure out what side of it gives you the less than scenario and what side of it gives you the greater than scenario. So if I put all these numbers in, 1.68 e to the negative 8 times 60 divided by pi, I'm going to take the square root and divided by 1. I'm going to take the square root of all that. And multiply that by 2. Then ultimately I run out of room, so what happens? I get 0. So I get D is 0.0011 meters. I think you can see that that's a diameter of 1.1 millimeters. Speaker wires are actually very, very small, by the way. You usually don't use big ones. So that would probably be very easy to do. Maybe you might even want to save a little bit more of your power to the speaker and maybe even reduce it to say 1/100th of an ohm or something, and then you'd have to get bigger and bigger diameters. But that does give us a diameter that would work for getting a resistance of less than 1 ohm. So if I did that one, it would be exactly 1 ohm. If I did larger than that, it would be less than an ohm. And obviously maybe a 2 millimeter diameter would give me way less resistance than I need. I could even go 4 millimeter diameter, which isn't even half a centimeter at that point, and you can get even better. The main way I figured that out is that by looking that the resistance and the diameter are inversely related. I use the thumbs up, thumbs down symbols for that. Okay, that means as the diameter gets bigger, the resistance gets smaller. So I know anything bigger than that's going to get me even smaller resistance. Does that make sense to everyone? Now, you might be curious what's actually going to happen if I actually take, say, let's say I considered a certain amount of amperage going through the speaker wire to the speaker. How much voltage drop would that wire be versus, what the typical circuit would handle? So, it's common, for instance, in a car to use a 12-volt battery. So your power supply is basically 12 volts. And then you might say, okay, well, I've got to deliver 4 or 5 amps to my speaker. So you then say, well, with this in mind, what would be the actual current going through the wire? Or more specifically, since I'm doing, let's say, 5 amps, I know the current. You might want to know, well, how much voltage drop exists across the wire? Well, across the wire, you're just going to use V equals IR. The R we found was going to be less than 1 ohm. So that's a good number we multiply it by. The current is actually going to be 5 amps. So if you had at 1 ohm, you'd have 5 amps times 1 ohm, and that would give you 5 volts. Your 12-volt battery is already taking a hit of 5 volts to get to your speaker. So basically 2.5 volts is going to be the drop between it and between the stereo and the speaker, and then another 2.5 volts dropping between the speaker and coming back to the battery. So you end up only getting 7 volts across your speaker. So that would be a bit of a bummer, and that's why you might even look for smaller amounts, because you probably want most of your voltage being across the speaker as opposed to across the individual wires. I got 2 more things I want to talk about. I think now's a good time to take a little break. So let's pause this and let's come back at 11. Okay, so everybody just come back at 11. I'm going to be here, so you can still ask me questions. I'm probably just going to have the camera off, but come back at 11, everyone, and we will pick back up where we're at. All right, everybody, I guess it's about time to start back. I have a question that says, I was wondering, along with the people in my lab group, if we can continue to be in the same lab group. It was me, Marianne, Shirdy, sorry. Yeah, I think that's fine. If I have any problems, if anybody tells me they're specifically not working well with a group, then just let me know, and I'll see if I can jumble those up a little bit. But generally speaking, I'll keep the same ones as best I can. You'll just have to tell me who was in the groups with you. So I see your group, for instance, Janice. So I'll keep those together. Anybody else lets me know what their groups were. When I break off into labs this afternoon, I'll let you guys use the same group. And like I said, if any one person has a problem, and it's not necessarily, I see that tooth, that looks so bad. It's not necessarily anything wrong with the individual person or the group. Often it's sometimes one group will be really fast, and then a student in that group was like, kind of got lost and didn't really learn as much. That's a perfectly good reason to switch to another group. Sometimes people are not necessarily that they're all overachievers and the other person's an underachiever. It's more like maybe those people have an experience with this, that maybe they had physics, for instance, in high school already, and it's just really hard for someone who's new to it to keep up. So by all means, let me know if you have any problems with that group that you're in, and I'll switch you out to another one. But we'll start that come lab. So thanks for that question, Janice. So we've got a couple more topics to cover. One, I want to talk to you about something I've already hinted at. I've already told you, for instance, when you heat up a material, basically the definition of temperature, which if you had thermodynamics portion already, you probably already know this, or you should already know this, but the very definition of temperature is the average kinetic energy of the random linear motion of the individual molecules and atoms that make the substance up. So if we went through your body and surveyed every molecule and atom in there and said, hey, how much do you weigh? All right, what's your average speed? And then I took that mass that the atom or molecule weighed, and I multiplied that by the square of their average velocity, and then multiplied that by 1/2, so I get the kinetic energy. And I did that for each of the individual molecules and atoms in your body, and I took that average and then basically multiplied it by a number or something, sort of that sort of thing. That would give me a number that's equivalent to the temperature of the object. For instance, for the average human, it might give 98.6 Fahrenheit. That is the definition of temperature. The higher the temperature is, the faster the molecules move, or more specifically, the bigger thing is that the kinetic energy of the individual molecules increase. So for instance, if the atoms and molecules are really big, massive suckers, their velocity doesn't have to change that much for the kinetic energy to change quite a bit. But the key thing is that average kinetic energy is a measure of the temperature of a body. So because of that, we know that when you heat up a wire that's going to carry a current, for instance, the individual molecules or atoms that are in that lattice, they're doing this, but if they get really hot, then they're doing this, right? And when they're doing that, then it's a lot harder for electrons to flow through. The electrons are bouncing around quite a bit faster as well, but it's really a lot less likely or a lot harder for an electron to run into an electron than it is for an electron to run into an atom. So generally speaking, we do expect the resistance to go up with an increase in temperature. We found that this is luckily a linear result, meaning basically the resistance at a given temperature is related to the resistance at another temperature through y equals mx plus b. It'll be a little bit hard for you to see the y equals mx plus b form for it, but I think I can give you an example that will actually tell you some realistic stuff that you might have actually experienced. So let's get cracking on that. Before I start, does anybody have any questions on what I just said? I think it'd be really cool if I had if I started smoking, I just stuck a cigarette in there and hang that out. That'd be bad then. I wouldn't look like the goober that I am. Oh well, let me stop fixating on that. I just can't stop looking at my stupid missing tooth. So I'm gonna go to the document cam. Hey, these are the jokes, kids. Tell me what other jokes you get in your physics classes. But Mr. Greer wasn't as funny. Or Mr. Ippolito. All right, here you go. So the way the resistivity of a given metal works is that the resistivity at a given temperature T is actually equal to some resistivity at some critical temperature, say 0, and that temperature could be literally 0 degrees Celsius, okay? That multiplied by 1 plus alpha, that's the temperature coefficient of resistivity, times the change in temperature, which would be the temperature T minus T0, which, like I said, might be 0 degrees Celsius. Well, that's fine. That gives you a relationship to find the resistivity of a given metal at a given temperature. The big thing is this works, and it's mostly true, but if you get too large of a difference between these temperatures, you might have to go up to another base. So for instance, if you're working around 10 to 20 degrees Celsius, then this will probably work fine if you're using this figure for 0 Celsius. But if you're starting to work around 40 Celsius, then maybe you need to look for one that has the rho 0 for 20 degrees Celsius. So, keep it within 10 or 20 Celsius of it, because it's not exactly linear. Like if you made a graph of rho versus temperature, it probably looks like this. So you can see over a small area, yeah, that's pretty linear. But if you take a bigger area, it starts to bow a little bit. So in general, this formula only works for a small range. So you should always try to find, or try to use this formula and then try to find the tabulated resistance that's closest to your temperature. So if you're dealing with 40 degrees Celsius, it would probably be smart to look up what rho 0 is, or what rho is at 20 degrees Celsius, or even 30 would be better. Okay, so the closer this is to your actual temperature, the more accurate your result will be. But at the end of the day, we hardly ever use that. We actually often use this figure, which is the resistance at temperature T, lo and behold, is equal to the resistance at some specified temperature, rho 0, R0, for instance. 1 plus, again, the exact same alpha times T minus T0 again. So it's the exact same formula, except instead of resistivity, you actually talk about the resistance. So let's say we have a coaxial cable. Has a resistance of 100 ohms, okay, at, let's say, 10 degrees Celsius, which was when it was installed. Does anybody know anything about coaxial cable? What do they use that for? Anyone? Anybody know anything in your house that they use coaxial cable for? There you go. Internet, cable, audio. Yeah, exactly. Most people know it from cable television, DirecTV, Dish Network, that sort of thing. So that's coaxial cable. So imagine that the guy comes out in a winter day. 10 degrees Celsius is about 50 Fahrenheit. So that's kind of chilly, not super chilly, but still pretty cold. So he comes out 50-degree day and he installs this coaxial cable from your satellite dish that runs to various TVs in your house. And on that day, the actual resistance of that length of wire, let's say from the satellite dish all the way to the farthest bedroom, say, is 100 ohms. Okay. What I want to know is what would be the resistance on a hot summer day where the wire reached, let's say the wire reached, so I use this mnemonic, 30 is hot, 20 is nice, 10 is cold, 0 is ice. So 30 in that scenario turns out to be 84 degrees Celsius, if I remember correctly, or excuse me, 84 degrees Fahrenheit, if I remember correctly. So let's go a little hotter than that. Let's say it's 35 degrees Celsius. We're going to assume, well, the wire did do that. We're going to assume the day is actually probably a little hotter than 35. There's always a lag between the temperature of the outside versus the temperature of the wires, because, a wire running under the house, it's usually a little cooler under the house than it is outside. If the wire was actually ran through the attic, though, you'd expect the temperature of the wire to actually reach that temperature and maybe even higher, because it gets quite a bit hotter in the attic than it does in the crawl space. So in principle, it's better for those cables to run under the house as opposed to on top of the house. But what I'd like to find out is, what is that resistance going to be at 35 degrees Celsius? Well, we know that the resistance at a given temperature T, which in this case is going to be 35, is equal to the resistance at some other temperature. So I'm going to treat this like a copper, say, and with copper, I'm going to use the coefficient of resistivity alpha Cu, which turns out to be 0.0068, 0.0068. And the units for that are reciprocal Celsius degrees. So that's Celsius degrees to the -1 power. That's the actual unit. And these are actually taken at 20 degrees Celsius. So I'll say 20 degrees Celsius. Actually, no, in this case, I have to do it relative to 10. So I'm going to say 10 degrees Celsius times 1 plus alpha T at 10 minus T at 35. Actually, I did that backwards. T at 35 minus T at 10. So that's what our formula is going to be. Generally, you could use it as any standard, but I already gave us an actual resistance at the 10 degrees Celsius. But in this case, it's smart for me to just use that. That is a long stretch. And in fact, what I lucked out on is I used alpha, and this is actually for 20 degrees Celsius. So this is really fortunate because this alpha at 20 degrees Celsius sort of falls within the range that I'm doing here. So that's probably a good alpha to actually estimate it with. So I'm going to determine what it is. The resistance at 35 should equal the 100 ohms, the 100 ohms times the 1 plus 0.0068 Celsius degrees to the -1 power. When you say Celsius degrees, that's supposed to be different than degrees Celsius. In other words, if you subtract 2 degrees Celsius from each other, like 35 degrees Celsius minus 10 degrees Celsius, you get Celsius degrees. Whereas if you just multiply this 0.068 times 35, then you get Celsius degrees times are divided into degrees Celsius. So that's why they put it in a different order. It doesn't matter too much though. So I'll do this is 35 degrees Celsius minus 10 degrees Celsius. Putting all this together using my calculator, I'm going to say this is 100 ohms times 1 plus, what I'm going to do is 0.0068 times, I'll use my parentheses and do 35 minus 10, which obviously is only going to be 25. But times 0.068 would be 1 plus 0.17. So I'm going to add that to 1, the 0.17, add it to 1. And I'm going to multiply that by 100. I think you can tell already it's going to be 117. So yes, when the temperature gets hotter, the resistance gets higher. And in principle, you could actually cause your speed of your communications to slow down. You're actually causing the resistance to go up. And what they sort of measure at the unit where you're actually reading to the TV, for instance, what they normally read is how much power is coming out of it using something like a decibels or something like that. So in fact, when you go from 100 ohms to 117 ohms, which isn't a huge difference, but it is 17%, when you do that, you're actually decreasing the number of decibels received. So it's not unlikely for you to have a slightly worse signal. That could be worse in the fact of communications. It could be slower. It could be lower resolution in the case of a photograph or photograph in the case of video or something like that. Anybody have any questions on that? All right, so the last thing I want to do in chapter 17, and then we're going to go to chapter 18, then we're going to go to chapter 19 and do a couple sections in there. The last thing I want to do is power. So you probably remember power from when you talked about work and stuff like that. Well, there is an actual power that we deal with in electricity. And basically, so far, we have a few equations. I'm going to recap them here. We have V is equal to IR. That's Ohm's law. That's very important. We have R, or let's do I first. I is delta Q over delta T. We have R is equal to rho L over A. And of course, this resistance, just like this alpha, is something that you have to either look up or on a test, they'll give it to you or something like that. We also have R rho at a given temperature T is equal to R at a certain standard temperature, 0, say, times 1 plus alpha T sub T minus T sub 0. So that's our equation so far. Well, it turns out if you actually want to figure out what the power is, power has always been work divided by time, which you can think of work as energy or something like that. But in terms of if you use some of the calculus, you could actually come up with a nice expression for this. But it turns out that ultimately power is equal to IV. So our big new equation is P is equal to IV, and that's sort of the same form as Ohm's law. It's a some number equal to a product. So this is another really big value. If you know the current and the voltage, you can immediately find the power. The power comes out in work per time. That would be joules per second, which we know is a watt. So this will come out in watts. But you can also say, try to figure out what the power is in the event that you don't know the current and the voltage. Maybe you just know the current and the resistance. If that's the case, then you can substitute V equals IR in for the V, and you get P equals I squared R. That's another helpful result. Or what if you know the voltage and the resistance, but you're not aware of the current? Then you could substitute V equals IR to get rid of the I. So that would become V over R. So you get, in fact, V squared over R. So that's the three main forms of power that we can use. This one right here is particularly important because it tells us why we use AC so easily, and in fact why we have those huge towers running through country fields with power lines really high up in the air, and why they're at hundreds of thousands of volts. So what we're going to do now is explain that. So it turns out when you generate electricity, let's say at a power station, maybe it's a nuclear fired power plant, or it's a coal fired power plant, or it's a hydroelectric power plant. It doesn't really matter. Basically, at the end of the day, the most efficient way we found to do that is by taking whatever source of energy we have, be it currents or wave action or nuclear explosions, nuclear reactions. All that stuff basically generates heat. We then let that heat boil water. That water boiling then goes through a turbine that basically spins it, and that spinning is basically connected to some magnets that spin through a magnetic field, creating current, and out comes 60 hertz power. And it's usually on the order of, obviously at least 220, because our 220/240 that comes to a house, but they can do other powers as well. But then they want to send it to a house. What they know is that the distance from a power plant to a given house is not something they can play with. It's not something they can adjust. They're not going to be able to bring the house closer to them. And the resistance, by the way, is proportional to that length of that wire. So really, at the end of the day, you're sort of fixed on losing a certain amount of power as a result of the length of the wire, the cross-sectional area of the wire, and the resistivity of the material. So it turns out that power is equal to the current going through it, through that wire, times resistance of that wire. And by expressing it this way, we have it in terms of something that we can't change. So the only thing we can change, for instance, is the I. So if we send this power out at, let's say each house normally has a 200 amp supply. That is typical for a home. They have a 200 amp source coming to their house. You can get as much as you want, but 200 amps is normally the service that comes into the house. So if you send out that power at 200 amps, you're going to take 200, you're going to square that. That's going to give you 40,000. Then times that resistance, you're going to get on the order, because it's, obviously several meters. You're going to get on the orders of hundreds of thousands, if not millions of joules lost to the wire just heating up. That's what this power is power being dissipated because the wire got hotter for that current rolling through it. And that power is just dissipated, completely lost. So what the power plants realize is, crap, the higher this current is, the worse it is for us to waste electricity. So we're getting, ripped off. We're actually selling power at a cost that's going to make the customer pay more, and it's going to actually, make us lose profits because obviously the more expensive you sell it for, the harder it is to sell it. So what they do is they figured out, well, it turns out if you up the voltage, then the current goes down by the same amount. And to do that, they use something called a transformer. Excuse me, I couldn't think of that for a second. And a transformer is more or less, you can think of it as those old belt buckles that kids used to use in the Thanksgiving play at school, where it was basically just a chunk of metal like this. So if you took a chunk of iron like this, and then you took the wire coming from the power plant and you wrapped it around this, let's say 1,000 times. So there's 1,000 turns around this end. And let's say you then took this side, and this is the wires going to your house, for instance, and let's say you did 100,000 turns on that side. Well, if this came in at, let's say 220 volts, then out the voltage is going to come 220. Since I went up by a factor of 100, it's going to be out at 22,000 volts. That's called a step-up transformer. So I just stepped the voltage up from 220 volts to 22,000 volts. But the cool thing is, the 200 amps that I was sending to your house just went down to 2 amps. Because voltage and current are sort of oppositely related when you go through a transformer. So what was going to cost us roughly 40,000 times, let's say the resistance of the wire was 1,000 ohms. So this is 4 times 10 to the 4th plus 10 to the 3. That's 4 times 10 to the 7th watts. By doing this, switching this 220 volt service to 22,000 volts, I reduced the current from 200 amps to 2 amps. Now I'm going to say 2 squared times 1,000 ohms. That's going to be now 4,000 watts. So in fact, I saved about a factor of 10,000 in costs. So this I squared R version is really important because it tells us that using high voltage power lines to go over huge country fields is much more cost effective than using low voltage but high amperage. The downside, of course, is that I can go out in that open field in the dark of the night and make a large loop of wire and then loop it around, say 100,000 times like this, and steal electricity from it, even without having the wire going through it. Like just the wire going over my head, I can steal electricity from it. But power companies are actually pretty smart, and they can tell where you're doing that. So if you do that once, you might get away with it. If you do it more, and it is illegal, by the way, so don't. But if you do that a couple of times, they're probably going to catch you, and you're probably going to spend a long time in prison. So don't do that. But that's one of the neat effects of the magnetic field that's created around the current carrying wire. That's why this transformer works. That's why you can steal electricity that way. So that's what power is. Power can be thought of as the current times the voltage. It can be thought of as the square of the current going through the object with resistance R times resistance R. R can be thought as the change in voltage across the wire divided by the resistance of the wire. Okay. Notice I couldn't use that formula and get a bigger number when I was talking about carrying that high voltage power lines all the way to another place, because I'd have to find out what the small voltage drop was. So I sent it out at 220 if I didn't actually use high voltage, for instance. If I send it out at 220, maybe it gets to the house at 219. So you probably see that wouldn't be that very that helpful. So we're not comparing the 220 to the 222,000 and that's why I use that formula. All right, so let's look at a typical example using power. So for instance, let's say, let's calculate the resistance of a light. Let's say we have a light. Typical light bulb might be 60 watts. Okay, so let's say you have a 60-watt light bulb and you're actually going to connect it to a 120 volt source. I might want to know what is the current going through that. So this is a typical 60-watt light bulb. I'm talking an incandescent one. So if you get a fluorescent, compact fluorescent bulb that's equivalent to 60 watts, it's going to use a lot less power than 60 watts. But if I take a regular incandescent bulb that's 60-watt rating, that means it's going to burn 60 watts. And the reason why we don't want to use those, and we do want to use compact fluorescent lights, is that the 60-watt bulb is actually going to burn all 60 watts, and maybe 6 of those watts or even smaller will go to actual visible light. The rest will go to heating up your room, which if it's in the middle of the summer, that's kind of bad, because you're paying the air conditioner, or you're paying the power company for your air conditioner to make the room cool, and then you put this light bulb in there and that's generating heat. So you're literally fighting yourself. So let's actually see, and I know, yes, the voltage coming in a house that you plug a light into is AC, but it turns out the formula P equals IV works for AC voltage as well. So let's do this. We have P is equal to IV, and I wish to know the current. Well, the current is just P over V. The power is 60 watts. The voltage is 120 volts. Obviously, I think everybody knows that 60 divided by 120 is 0.50, and that's going to be amps. So a 60-watt light bulb with 120 volt power source coming into it uses about 0.5 amps. Does that make sense? Now you could also try to figure out what the actual resistance of that light bulb is, like we did before, and this would just cause us to use Ohm's law, V equals IR, and you say, okay, well, R is going to equal V over I, but V is 120 volts, and I is 0.50 amps. Obviously, 120 divided by a half is the same thing as multiplying by 2, so that'd be 240 ohms is the resistance of that light bulb. But notice you also could have used, to figure out that, you could have used P is equal to V squared over R. In that case, it would have been 120 squared over R is equal to the power, which is 60 watts. And you just solve for R. In that case, you get R is equal to 120 squared divided by 60. And lo and behold, you get 240 ohms again. Okay, so you can see there's a lot of different ways to solve these problems. They usually give you, a certain information, and when you go to try to solve it, there's actually more than one way you can do it. So don't be, upset if you do it one way and, someone that you are talking to in your class does it a different way. They both might be right. And in fact, that's a good thing to check, because whenever you do it one way, it better come out the right way with the other equation as well, or something's wrong with one of those two methods. Okay. I think that's about it. Yeah, that gives you a pretty good understanding of basically how power is dissipated in a given circuit, how to use that equation. You can look for other examples in your textbook and stuff like that, but we got a couple more sections that are really going to be short, and we're going to discuss those directly. Specifically, we're going into DC circuits. So, and by the way, your textbook, as many other textbooks do, it opens up with a concept question. Those are really good concept questions. I highly, highly, highly recommend you actually trying to guess what the answer is even before you read the material. And then later on, once you've gone through the material, it sort of recaps and says, now you know the answer to such and such. So you can learn from that, and you can learn how to think, and it's actually sort of like an experiment going on in your head. So definitely, definitely, definitely do those. I'm going to start off with talking about EMF and terminal voltage. So before we talked about a battery, and I showed you a drawing of a battery. I said you basically had this chunk of metal here, that inside of which was a carbon rod, which if you watch The Simpsons, you know that one employee of the month before Homer Simpson did. Basically a carbon rod won it. Sorry, I'm a Simpsons fan. I got to bring it up every time I can. And then there was a zinc cup that held an electrolyte paste. So you can sort of think of it as Gatorade. So Gatorade would be a usable, if not non-ideal, but it would be a usable electrolytic paste in here. Well, it turns out over time, batteries die. And as they die, what we recognize is this battery that when I first opened it up, whether it's a D battery or a C battery, a AA or AAA, when you first open, or even a 9-volt, when you first open it up, in the case of A, AA, C, and D, it would read about 1.62, 1.65 volts, something like that, but it advertises a 1.5 volt battery. As time goes on, it's slowly going to lower that voltage when it's connected to a power source. That voltage will lower below even 1.5. Once it gets below 1.5, it's sort of no longer usable. People can use it. It's just not going to be as working as properly in whatever device that, if it's highly dependent on the voltage, isn't going to work as well at 1.4 volts as it does at 1.5. So we try to model this as what could actually happen. And in doing so, what we've decided to do is we basically take a battery like that and we represent it as long line, short line, long line, short line, or even just two, that'd be fine. But before we get out of here, before we get to this point right here, from this point, which this point is the same as the bottom here, we say there's an internal resistance, little r. Okay, so now this point and this point are the same, and this point and this point are the same. And then if you want to connect that to a circuit, you'd say, okay, well, here's my load, big R. Well, what that does is, notice this voltage will always be, if it's a case of a AA or C or D, it would always be 1.5 volts nominally. If it's a case of a 9-volt, it'd always be 9, but you know when you first open it up, it's probably going to be 9.9 or something like that. In the case of the A, the C, the AA, all those batteries, it'd be 1.65 or something. But as this battery gets older and older, this resistance gets larger and larger. And that means that the voltage across here, from here to here, which started off at 1.5 and should come out as 1.5 because this is so small, that's going to be getting smaller and smaller. So by modeling a battery that way, we can actually treat it more realistically. And what we call this 1.5 volts is called the EMF are electromotive force. It's not really a force, it's voltage, okay? But for historical reasons, we still call it an electromotive force. So that's what this is. So when someone says a battery has an electromotive force of 10 volts, then that's a 10 volt battery. But then they'll tell you it has a resistance of 1 ohm. Then you know that over time, that 1 ohm resistance will slowly get larger and larger. And then the terminal voltage of the battery, which is the voltage from here to here, not from here to here, the terminal voltage will actually seep below the 10 volts that you wanted it to be. So let's imagine, for instance, that we have, let's say we have a 100 ohm resistor connected to the terminals of a so we're going to connect this to a battery. I really like to use pretty easy numbers. So let's say this is a 12 volt battery of a 12 volt battery. And let's say that that battery has a internal resistance of let's say 0.30 ohms. Okay. So the battery has an internal resistance of 0.30 ohms. What I want to know is calculate the current in the circuit. I want to calculate the terminal voltage of the battery. And then I'd like to find what the power loss is in both of those resistances. Okay. So A, the current is question mark. In other words, I want to know the total current I going through it. So it's just like this, but I just say the current I. B, I would like to know what is the terminal voltage of the battery. So I'll say V terminal is question mark, and I'll show you how to do that, of course. And C, I'd like to know the power loss in R and in big R. Okay, so in other words, the load is going to be the big R, the little r is going to be the terminal resistance, or excuse me, the internal resistance. So here's my circuit. I have an EMF. Obviously, they're talking about a 12 volt battery. So my EMF, which is given the symbol this, is equal to 12.0 volts. But that is in series with an internal resistance of 0.30 ohms. And there's the end of my battery. So I'll draw a sort of battery around it, if you will, just to give you a physical idea of what's going on. Now this comes out and connects to a resistance R equals 100 ohms. Okay. The current I, again, we're treating it like a conventional current, is that. So for part A, I know that V is equal to I times R. Well, you don't necessarily know this now, but that's something we're getting ready to learn. It turns out the total resistance applied to this voltage V is this resistance plus this resistance. So the total resistance is 100.3 ohms. So if I want to know the current, I'm going to take and divide the voltage, which is 12.0 volts, by the total resistance, which is 100.3 ohms. And I'm going to get something very, very close. Very, very close to 0.12, but it isn't going to be 0.12, and that's sort of the point. So I'll do 12 divided by 100.3, and I get 0.11 0.96. I'm going to write a couple extra digits here just so you can see that it is, in fact, close to 0.12, but it is not 0.12. So in milliamps, I could say this is 100 and obviously you can see even in the third decimal place, I have to technically round it to 0.120 milliamps, but I'm going to keep an extra digit just so you can see that it's different, 19.6 milliamps. So that's actually the current, 119.6 milliamps. That gives me part A. Part B, I want to know what the terminal voltage for the battery is. So what's going to happen, as I told you before when they opened up on the last chapter, the voltage right here is going to be 12 volts. The voltage right here is going to be 0 volts. And I'm essentially going to assume it's 0 all the way along here, all the way to there. That's because I'm ignoring the resistance of this wire. In principle, this has to be slightly higher than 0, and this reaches 0 right there. Then this would be 12, and it get lower and lower and lower and lower and lower, and then it'd take a big drop lower, well, a bigger drop lower, but still quite low, and then lower and lower, lower, and then lower, lower, lower. So it'd actually be quite a bit less than 12 by the time it got here. But in fact, we're going to pretend like it reaches pretty close to 12 there. And by evaluating Ohm's law for this resistance, we'll see exactly how far it did change. Again, ignoring the resistance, but taking into account the resistance of the wires, but taking into account the internal resistance. So if I pretend the wire is 0, then this will be 12 volts here. And it's going to be 12 volts here. Okay. And this will be V terminal. In other words, if I put the black wire on the voltmeter on the back of the battery and the red wire here, 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 or here, or even here, that'll be the voltage VT. And that's what I'm reading right at that point. Well, it turns out the voltage drop across this is just equal to the current through it times the little resistance. Well, the current through it is equal to 0.119641, keeping all those extra digits just for the heck of it, times the internal resistance, which is 0.30 ohms. In that case, I get times 0.3, 0.035892. 0.035892. Just keeping extra digits again to give you a feel for what's going on here. Volts. Now we're really only supposed to use 2 sig figs, so I should be calling this 0.036. So V across the resistance is 0.036 volts. So what that means is the voltage went from 12 to 12, and then 12 minus 0.036. So V terminal is actually equal to 12.0 volts minus V internal resistance, which is 12.0 volts minus 0.036 volts, which isn't even in the significant figures. Notice that's the second decimal place. We only go to 1 decimal place. So technically I'd have to call that 12, but to show you that it actually does have effect, I'm going to subtract that. And I get 11.9641 volts. So the terminal voltage is about 11.96 volts. Notice that 1 decimal place, which is what I should round it to because that's 3 sig figs, and then that would be 3 sig figs, I would still get 12.0. But I have to show you that extra digit so you see that, in fact, the terminal voltage is slightly less than 12. So that's our terminal voltage. The last part, we would like to know the power dissipated. So power dissipated by R is just I times V. But in doing that, I'm actually calculating the voltage. I have to use the voltage that I just calculated. There's a chance I might have some error there. So wouldn't it be better to use something I didn't use or I didn't calculate? Well, you can't really get around that here because I actually calculated the I too. So it would be better to use less things that I calculated. Since I calculated the I and I calculated the V, that's sort of doubling up my chances of error. So it might be better to use I squared R. So I'm only using one thing I calculated. So I'll use I squared R for my power. Well, the current we found was 0.119641 amps. I'm going to square that and multiply it by 0.30 ohms. And then I can go back to the regular sig fig things. 0.119641. So I get 0.0043 watts is the power dissipated by the internal resistance. Now the power dissipated by the actual 100 ohm resistor is actually equal to 0.119641 amps. In this case, I could use the voltage R. I'm going to choose to use I squared R again because I is something I calculated, but R at least is something I know. So I'm going to say the R in this case, which was 100 ohms. Obviously, I can do this math in my head. This is 11.96. Ooh, no, it's not 11.96. I've got to square it.
Put that up a little. I can't see where you're writing.
Oh, thank you. Thank you for that. Yeah, 11.9641 is what I got already multiplied by 100, but that was me not squaring it. So I'm going to remember to square it.
Where'd you get the 100 ohms?
That was originally given in the problem. We have a 100 ohm resistor. Remember
Okay.
that?
Yes.
Okay. So 1.119641, I square that and then multiply it by 100. Now that part I could do. That's 1.43 watts. So yes, the actual load resistance dissipates the vast majority of the power, 1.43 watts, and the internal resistance generates very little power loss, which is sort of the point. You know, you don't want a battery that's so horrible that it actually gets really, really hot. And in some sense, when you actually are using a battery, you'll notice, for instance, the back of your cell phone gets kind of hot after you used it for a while. It also does it when you're charging it. What you're feeling is, or what you can imagine feeling, is the internal resistance of that battery getting hot because it's got to dissipate the power that has been delivered to it. So whenever you have a resistance, it's going to basically seep out heat, and that heat is basically getting rid of the power dissipated that we've now learned about as P equals IV. Does that make any sense? The big thing that you got to learn here from this, in general, the voltage at the terminals is equal to the EMF minus the voltage across the internal resistance. So that's the main big thing that I used. I didn't give you that formula. I didn't really use that formula. I just explained it to you by talking about how the voltage is going to slowly get smaller and smaller and smaller. And then it gets to this, and it's going to make a big jump compared to the wire, but it's still a small jump compared to the jump across here. So when it gets way across here, the jump is going to be quite small. In fact, if you wanted to, you could find out what that jump is going to be. 11.96, in fact, is what it is, because essentially 11.96 is the voltage here, 0 is the voltage here. And yes, it's going to get smaller and smaller than 11.96, but we're ignoring the wire resistance. So it should be very close to 11.96 here and very close to 0 there. So that is the ultimate voltage across the 100 ohm resistor. But that formula is something that you got to think about when you're dealing with batteries. It's always the EMF, which is sort of like the voltage of the ideal battery with no internal resistance, minus the voltage across the internal resistance. And you got to remember that VR is just given by Ohm's law, where I is the current you calculate and R is the internal resistance. but I, the current you calculate, we can tell, remember we did V divided by the sum of the R's. So it should be V over R plus R times little r. So just remember, you've got to first calculate the current through it, remembering that the resistances add, and then that gives you the current. You multiply that times the resistance of the internal resistance, and then subtract that from the EMF, and that will give you the terminal voltage. So this is something that we do over and over again in physics. So I just want to make sure you guys can make sense of that. All right, the very last topic. And we're about running out of time anyway, so that works great. The very last topic is resistances in series and resistances in parallel. So you first need to understand what we mean by a series. And let me give you a diagram to help you figure that out. So I'm going to take a battery and I'm going to connect it to a wire. And then I'm going to run that wire through one resistor. And then I'm going to take a wire out of that resistor, and I'm not going to give any more choices. In other words, every single imagined positive charge that comes out of this terminal has to go through that resistance. It doesn't have an alternate path, okay? And then it leaves that resistance and goes into another resistance, and it has no choice about that either. And then it leaves that other resistance and goes through yet another resistance, R3, and then all comes back. So when you have the path for the imagined positive charges going around, when you have it automatically set where it has to go through everything, that is a series circuit. Meaning you have to go through 1 and then 2 and then 3 in a series, okay? Now, if on the other hand, I had a single battery right here, and the wire came out and it had a choice. It could go through R1 and then return back to the battery, or it could go through R2 and then go back to the battery, or it could go through R3 and go back to the battery. And this would be the nth resistor, for instance. If it was set up like that, then each positive charge has a path to choose every time. And in fact, it has a number of paths. It can go through R1 or R2, or it has 10 n different ways it can go. That's called a parallel circuit. Well, I think you can figure out that every single bit of charge that leaves here has no choice but to go through R1, R2, and R3. So that means the current through R1 has to be the same as the current through R2, and that has to be the same as the current through R3. What I would like to do is find an equivalent resistance that I could replace all n of those with, and have the battery not know any better. In other words, have the setup where the battery is set up this way, but it can't tell whether it's set up this way or set up this way, where this resistance is called REQ, meaning equivalent, okay? So I'm trying to look for one resistor that I could replace all these guys with. Well, what I do know is this. I know that in this circuit, the voltage is V, and that V is equal to I, the current going through it, which is really the only way the battery knows what it's sending its current through, is through how much current it goes out. That's equal to I times R, okay? But I also know that V1, the voltage across resistor 1, is I1 R1. And I know that V2 is I2 R2, ... Y'all agree with that? That Ohm's law applies to each of those resistors? So it's just a matter of realizing now that because Ohm's law applies to each resistor is going to have a voltage drop V1, a voltage drop V2, a voltage drop V3, a voltage drop 3 on up to Vn, right? So when I get back here, I'm going to be 0 volts, but when I started here, I was at V volts. So that tells me that V has got to equal V1 plus V2 plus V3 plus ... plus Vn, where Vn is the voltage across the nth resistor. Does that make sense to everyone? That's just those bubbles I kept drawing. So basically I'm saying I got V volts here. Excuse me, I got V volts here. When I get here, it's still V. When I get here, it's V minus V1. When I get here, it's V minus V1 minus V2. And here is V minus V1, V2, minus V2, minus V3, and so on and so forth. Until the end, I get V minus V1, V2, V3, ... on up to Vn. And that's equal to 0. So you find that V has to equal V1 plus V2 plus V3 plus Vn. Does that make sense to you guys?
So it's not V1 minus V2, or is it?
So what conclusion I reached here was V minus V1 minus V2 minus V3 ... minus Vn. That's now equal to the voltage right there, which we said was 0. So now I can get this equation. Just by putting all those positives over there, I'd see that V is equal to V1 plus V2 plus V3. Does that make sense?
Yes.
Okay. So what we just discovered is that voltages add when you go around the loop. Now I can take this formula and put it over here and say I times R equivalent, because that's really what this was for this circuit, is equal to I1 R1 plus I2 R2 plus ... plus IN RN. But conservation of charge told us that, you know, if 100 charges leave this in a single second, then 100 charges are going to have to go through this, then 100 charges will go through this, then 100 charges will go through this. So I1 is equal to I2 is equal to I3 is equal to I. So all these I's are the same. I can divide them out. And I end up getting R equivalent for a series is equal to R1 plus R2 plus R3 plus ... plus Rn for any number in resistors. So when they're in series, they just add up, which I actually used earlier when we did the battery with the internal resistance and the load R. What's that now? You need me to move that?
Thank you.
Okay. Okay, so that's the resistance there. Now we're going to do the same thing for this setup, okay? But it's a little different in that what we have here is every charge that goes out of here. Let's say 400 charges came out of here. Well, one possible configuration is that 100 go through here, 100 go through here, 100 go through here, and then the last 100 goes through this RN, meaning there's only 4 instead of, you know, N is 4 in this case. That's a possibility, but the key point is it has to be true that the charges that went through this, plus this, plus this, and plus this, all those charges have to add up to the charges that left here. So if I wanted to replace this with an equivalent resistance, R equivalent, then I have to realize that I is equal to I1 plus I2 plus I3 plus ... IN. So does that make sense to everyone? Meaning, you know, if 100,000 charges came out of here and I had 100 resistors, if all of them were equal, symmetry would suggest that 1,000 charges, or excuse me, 1,000 charges is going to go through each of the 100 resistors. And that's just conservation of charge. If it didn't happen that way, some must be leaking out somewhere, are just sitting there not moving, and that doesn't make any sense. So we know that the total current leaving the battery must be equal to the sum of all the currents going through all the individual resistors. So what I have to make happen is I have to make this battery think that it's just one resistor over here that's exactly the same as that over there. So that's where we're going to start off. Well, we know that V is equal to I times R equivalent, just like we had before. Ohm's law applies, right? We also know that the voltage across here is V1, which equals I1 times R1. And the voltage across this resistor is V2, which equals I2 R2. So you can continue on, and you get Vn is equal to In Rn. So we can solve for all these. We'd say, oh, well, I is equal to V over R EQ. I1 is equal to V1 over R1. I2 is equal to V2 over R2, right? So what we have is V over R equivalent, putting it back in this equation right here, and putting it where y'all can actually see it, because that might be helpful. So this part becomes V over R equivalent is equal to V1 over R1 plus V2 over R2 plus Vn over Rn. Now here's the big mystery, and this is actually why your house is wired the way it is. It turns out if this voltage is, let's say 12 volts, and this voltage is 0 volts, ignoring the resistance of the wire, I think you all see that this voltage right here would also be 0 volts. Y'all agree with that? That voltage right there is going to be 0 volts because we're ignoring the resistance of the wire. And then this voltage right here would be 12 volts as well. Well, I was watching that on TV, writing it with my hand, and I'm not quite that good yet. And I think you then see, well, this one's going to be 12 volts as well, and this one's going to be 0 volts, and this one's going to be 12 volts, and this is going to be 0 volts. Does that make sense to everyone? And even if we didn't ignore the resistances of the wire, whatever the voltage is here, it's going to be more or less the same here, 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 and here. So in fact, what we find is that V, just plain V, is equal to V1, and that's equal to V2, and that's equal to V3, on it to Vn. So now I've got the expression for the equivalent resistance in series. 1 over R equivalent, or excuse me, in parallel, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus plus 1 over Rn. So for any number of resistors, you just add the reciprocals and take the reciprocal of that answer, and that'll give you the equivalent resistance. Let me show you how that works out. So if we have, so here's 2 quick examples, and then we'll call it a day. So if I put 200 ohm resistors in series, according to this formula, R equivalent series would equal 200 ohms. But check this out. If I put 100 ohms in parallel with a 100 ohm resistor, then 1 over R equivalent parallel is equal to 1 over 100 plus 1 over 100, which equals 2 over 100, which means R equivalent parallel is equal to 100 over 2, which is 50 ohms. So what we discovered, and this is actually the result, any number of resistances that you have in parallel, the resistance of the whole will be smaller than the smallest resistance in it. And any number of resistances that you have in series is always going to have an equivalent resistance. That's the sum of all of them. In other words, bigger than any of them. Okay. So resistors in parallel reduce resistance, and resistors in series increase resistance. But the reason that we wire our house, if you actually opened up, for instance, the wire that they use in your house, there'd be a housing like this, and you'd open it up and there's one wire that's either bare or sometimes it'll be green or something like that. That's the ground wire. And then there's another wire that's black, and then there's another wire that's white. And this could be green or bare. Okay. When you actually wire a receptacle, which looks like this, okay, this wire goes to one side, this wire goes to the other side, and this guy goes to that little hole right there. And then the next receptacle, long side, short side, little mouth like this, that wire goes to this side again, and that wire goes to this side again, and this wire goes to that thing again. So what we have is one wire that touches sort of the left-hand side of every resistor, just like one wire touches the left-hand side of every resistor. And the other wire touches only the right-hand side of every resistor. So houses are actually wired in parallel for the same reason that modern-day Christmas lights are wired in parallel. Specifically, if they were in series and that resistor burn out, then no current could flow whatsoever, so everything on that circuit would die, would actually get no electricity. Whereas when this is the case, if everything's on the air, one of them goes out, that's okay. All the other ones will continue to run. And it fixes them all to be at the same voltage, which is why I was able to make the conclusion that V was equal to V1, was equal to V2, was equal to V3, was equal to Vn. That all of that came from that basic principle. So the big things that we learned are series. All currents equal. And resistances add. And voltages add. Okay? In other words, if you want the resistance of all the resistance in series, you go R1 plus R2 plus R3 plus and so on and so forth. If you want the voltage across all the resistors in series, you go the voltage across the first one plus the voltage across the second one plus the voltage across the third one. Add them all up, and that gives you the voltage that the battery was supplying. Alternatively, in parallel, all voltages are equal. One over R equivalent, and I'll put a P on it, is equal to 1 over R1 plus 1 over R2 plus ... 1 over Rn. And voltages are all equal. Oh, I already said that, sorry. Currents add, which means I total equals I1 plus I2 plus I3 plus ... In. Okay, so those are sort of your golden rules for dealing with parallel and series circuits. All the voltage, all the currents are equal in series. all the resistors add up to give you the total resistance, and all the voltages add up to give you the total voltage. In parallel circuits, all the voltages are equal. The reciprocals of the resistances add up to give you the reciprocal of the resistance, and all the currents add to give you the total current. Okay. So we are done with section 19.1 and 19.2. I got a question about my YouTube channel, which I evidently sent out the wrong link. I will get that YouTube channel and email it to y'all this afternoon. Right now, we are done with the actual lecture portion. Lab is supposed to start at 12. Actually, no, we're actually a little early. Lab is supposed to start at 12:30. No, it's actually supposed to start at 12, if I remember correctly. Yeah, 12 exactly. So I'm going to give you guys, let's say a 20-minute break. We'll start at 12:30. It's actually a 19-minute break. We'll start lab, and I'm going to go ahead and kill this one because this meeting is for lecture. I'm going to kill this one and start the lab meeting at 12:30. Does anybody have any questions before I let you guys go? All right, I'm going to also have to post the lab that we're doing, so I'll go post that real quick too. But I am going to go ahead and close this. I will see you all in a few. Did somebody say something? They had a question?
Yes, I have a question.
Yes.
So I joined the class late, like probably Friday, so I wasn't in a group for lab. I don't know if you guys do new groups every time or the same group.
Yeah, no problem. What's your name?
Rihanna Garcia.
Rihanna, okay, not a problem. We'll find a group for you. That's not a big deal at all. You just won't, obviously because you weren't in the group Friday, so you won't have our Wednesday it is. You won't be in any group that you've been in before, but it's not a big deal. I usually use a random setup, but some students wanted to be in the same group they were last time, so I'll just put you in one of the other groups, and if it doesn't work out, you just let me know and we'll find a different group for you. Okay?
Okay, thank you.
All right, see you, Rihanna. Bye, everyone.